All right, in this video I want to continue looking at the second law of thermodynamics, but I want to look at cycles and compare what makes a cycle possible to what makes a cycle impossible. And first of all, I want to introduce sort of a little picture math of the way to think about cycles. Really, a heat engine, it brings heat into the system, say the boiler in that picture we had in the last video. It's going to produce power, so the net work will be out of the system, but there's going to be some heat loss. It was a condenser in the cycle that we looked at briefly last time. A refrigerator, or sometimes I'll treat it as a heat pump, depending on my goal, brings heat into the cycle at a cold temperature. Okay, so this is going to be positive, but at the low temperature. It's going to bring work in, and it's going to then send heat out of the system. So these are both devices that are possible. And we've characterized anything that creates power is a heat engine. Anything that requires power is a refrigerator, or sometimes we'll call it a heat pump. So let's look at one of the first statements of the second law of thermodynamics. This is the Clausius statement. And it's sort of a strange sounding explanation of the second law, but what it tells us is about limitations, and that's really what the second law is all about. It's different ways of analyzing the limitations we have. So this one says it's impossible to construct a device that operates in a cycle and produces no effect on the surroundings other than the transfer of heat from a colder body to a hotter body. So I cannot basically create a refrigerator that takes heat out of your cold food and puts it into the warm surroundings, because if I do that, I have to have work input. So a Clausius statement says you can't build a refrigerator that doesn't have work input. Okay. Now there's a very similar one called the Kelvin-Planck statement. This one says it's impossible to construct a device that operates in a cycle and produces no effect on the surroundings other than producing work and exchange of heat with a single reservoir. So in other words, if I bring heat in and then produce power using that heat, this isn't possible. I must also have some heat loss. Sure, I could build a device that did this, but it's not going to operate in a cycle. It won't come back to the original state. So my heat engines that produce power will bring heat in, fuel, but they also are going to have some waste heat, always. So these two statements, although they seem a little silly at first, what they're doing is telling us our limitations. I can cool objects off. Sure, I've got a refrigerator. I know it's possible, but only if I provide power input. I can turn heat into work. I do this every time I turn on my car. I am bringing fuel or heat energy into the vehicle and producing power that makes me drive my car, but there's always going to be some heat loss. Okay? Now what this tells me for thermal efficiency is that QH is always going to be bigger than W. I'm going to have a QL to be able to balance out and get to my net work. So the thermal efficiency has to be less than 1. Now, if these are both positive quantities, it also has to be positive. So these statements, as trivial as they seem, they actually are telling me that the thermal efficiency, net work over heat transfer in, is trapped between 0 and 1. Now, sometimes it's interesting to consider, I've got these two things and I said they're both statements of the second law. They really are, because they are equivalent to each other. And we'll have a lot of other statements of the second law before the semester is over. And really they all boil down to being the same thing. Now, for these two, it's easiest if you look at it using picture math. So you take a possible device, such as a heat engine here, okay, heat in, work out, QL out, and I add an impossible device to it. Okay? So, possible plus impossible. Well, this time I want to design one so I add a Clausius device. So I'm going to have heat going into the cycle that balances out QL, and heat out of the cycle that balances out QH. And if I add these two together, well, my energy balance, or first law, says that the net Q is going to always equal my net work. If my net work is 0, then QL equals QH, right? But I want to size this so these two are exactly the same, and then these two will sort of cancel each other out somewhat, but not totally, because QH is going to be the same magnitude as QL, just opposite directions. And so if I think of these as vectors, okay, then I'm going to have QH. It's smaller than what I had originally thought, maybe I'd be able to achieve, but it's going to balance with my work if the first law still holds. But if this was impossible, possible plus impossible, you guys know, if you have something that's real and you add something magic to it, you're going to get something magical or impossible. You could also do this by taking a refrigerator and adding a Kelvin-Planck device and end up with a Clausius device. So in our next video, we're going to look at things about reversible processes and start discussing what are more of the reasons, the physical reasons I have limitations, and then do some thought experiments about things that are unimaginably perfect.